like I mentioned before, we're just going to first figure out what the escape velocity from Earth would be. So to start out, we're going to first write down our kinetic energy term. So we know that we have kinetic energy as a function of time. And we also know we have to add potential energy, which is the gravitational energy of the Earth, as a function of time. This is going to equal some constants, like we saw before, that I'm going to call E total. E total is going to be equal to 0, because by doing this, we will figure out the velocity at which something will be able to escape Earth. So I'm going to cross out the E, and I'm going to set this equal to 0. So first I'm going to write the equation for the kinetic energy, which is 1/2 mv squared. And the equation for the gravitational potential energy, which is negative g, capital or big M, little m over r. And again, this is set equal to 0. So to make my life easier, I'm going to add a g mm over r on the left side, and also a g mm over r on the right side. And I did this so that I can, so that these two pieces of my equation will cancel out. So now that we've canceled out these two terms, and we have a gmm over r on this side, I can write this equation out again to see it more clearly. Have mv squared equals g mm over r. So we have this little m, which is the mass of our little comet or spaceship, whatever that's leaving Earth, on both sides. So what we're going to do is we want to cancel these out. So we can divide each side by little m, and that will cancel these terms on either side. And we will be left with 1/2 v squared equals g big M over r, where big M is the mass of our planet. So our goal, again, is to solve for v. So in order to isolate v, what we want to do is get rid of this 1/2 that we see here. So to do that, we can multiply both sides by 2. And by doing that, we can cancel these 2's here, and we'll be left with v squared equals, I'm just going to bring the 2 in front because I think it looks prettier, but it doesn't matter. 2gm over r. This is also a multiplication all at the top. And then now to get rid of this squared, we know that the opposite operation of a power law is a square root. So what we can do is take the square root of both sides. So I'm just going to put a square root sign here and a square root sign here. And by doing that, I'm canceling out the power and the square root, since they cancel each other out. And I will be left with velocity equals the square root of 2g m over r. Now we have some values for these, for each of these terms in our equation. So we can replace those in this equation now, and we have the square root of 2. So we have our g, and that's equal to 100. And our mass of the Earth was equal to 1,000, which we divide by radius, which we had set to be 50. So now we have this equation. And we can either put this in our calculator or do mental math, whichever you prefer, and we'll get that the answer for the velocity will actually be 63.25. So this is a velocity that you will need to escape Earth's gravitational field, with having Earth as a mass of 1,000 and our gravitational constant g set equal to 100. In our program, we found out empirically that the velocity should be around 65. And we found out that the actual velocity should be 63.25. So we can find how off we were from the actual value by doing a fractional error. So to do that, we can, I guess I can do it here. So I'm going to say fractional error. I'm going to call it FE. Is that okay? So I'm going to call the fractional error FE. And this is going to be equal to the absolute, so this is going to be equal to the absolute value of the V actual minus V found divided by V actual. And we're going to multiply this times 100. So in this case, V actual is 63.25 minus V found, which was 65, divided by 63.25, and this times 100. Okay, so after plugging this into our calculator, we get that our fractional error was 2.7%. Right, that means that we were only 2.7% off from our actual value, which means we came pretty close to it.